All right, here we go. Week 4, Lesson 4, Mossbauer spectroscopy. This is a pretty specialized form of spectroscopy, but it's kind of cool and I like talking about it, so we're going to go through it pretty quickly and just sort of give you a sense of some of the interesting different spectroscopies that are out there for the inorganic chemist to use. This form of spectroscopy is really only used for iron. There are other elements that you can do this with, but iron is certainly the most common, and that's convenient because iron is pretty abundant in biological systems, and being able to observe iron in different environments is a good thing. So the basis of the technique is this. You have nuclear absorption of gamma ray photons. We're looking at absorption of gamma rays causing a nuclear excitation. We can then probe the nuclear energy levels for iron nuclei, and this gives us isomer shifts, which is like the chemical shift. So the isomer shift for these species ranges from 0 to 0.1 millimeters per second for an iron 4 to greater than 1 millimeter per second for an iron 2 that has nitrogen and oxygen ligands. So higher oxidation state of iron removes d electrons, it decreases the screening of s electron density and gives a lower isomer shift. The units of that isomer shift are millimeters per second, and I'll explain that on the next slide. So that's the general feature of the technique. The next thing is the quadrupolar splitting, which is like J coupling in NMR. So this also depends on the s orbital electron density and the electronic field due to nearby atoms. Okay, so the source for the gamma rays that are absorbed by the nucleus is a cobalt-57 nucleus, which is a relatively stable isotope of cobalt, which has a half-life of about 270 days. The cobalt nucleus decays to an excited state of iron-57, which then emits a gamma ray as the nucleus relaxes to the ground state. That gamma ray goes from the source to the target, and it's absorbed by the target. The textbook goes into some more detail about this, but the relaxation of the cobalt-57 would result in an energy that was lower than expected because some of the energy would be lost to recoil of the nucleus. So kind of like when you fire a gun, the bullet goes out, but the gun is pushed back. The source would be pushed back by the loss of the gamma ray, and then the absorber, when the gamma ray hits it, it would absorb some of that energy. And these nuclear energies are so the energy differences between the nuclear energy states is so small that would actually move it outside of the range that you could observe it. So what happens is the source has to be in a solid state, so it's in a foil, and the absorber is also in the solid state. And then it's called a recoilless transition, and the gamma ray comes out and is absorbed by the iron nucleus. This gives a very sharp resonant transition instead of a broader transition that would occur in the liquid or the gas phase. Now, the source has the iron atom, the decayed cobalt turns into iron. The iron is in a foil, and the absorber, let's say we're looking at a heme, that is not a foil. That is a solid heme iron in a frozen solution. And so the difference in these two environments is what gives us the energy difference. And it's a small enough energy difference that you can actually observe the difference by using the Doppler effect. And so the change in energy of that gamma ray can be observed by moving the source back and forth along a track, and then you can have the gamma ray with different energies being absorbed by the iron nucleus and the target. For a linear track, this cosine theta term just goes to unity, and so you can just have this velocity over the speed of light, and that source motion in millimeters per second is why this is reported in millimeters per second. So as you're moving the source back and forth at 1 millimeter per second, then you're absorbing the light, and you can report it in that way. Okay, so here is our excited state, iron 57, drops down in energy, a gamma ray is released, it hits the target, and it's absorbed. And in iron, because it's a quadrupolar nucleus, you actually see two different bands, the plus or minus 1/2 and plus or minus 3/2 states split the energy into a doublet. So you see two different transitions from the ground state up to those two excited states. The magnitude of this delta E that you're observing correlates with the degree of asymmetry in the electric field. So for an iron 3, a high-spin iron 3 with 5d electrons, that gives a spherically symmetric electronic configuration, so this delta E is low, on the order of 0.5 to 1.5 millimeters per second. On the other hand, iron 2 with similar ligands has a non-spherically symmetric electron configuration, and the delta E is on the order of 1.5 to 3 millimeters per second. Additional magnetic hyperfine splitting can also sometimes take place, and that's shown in this picture. So in the presence of a magnetic field, so that could be an unpaired electron on the iron center, or for a diamagnetic sample you could apply an external magnetic field that splits the 1/2 and 3/2 states into multiple states, and you can see a 6-line pattern. It's not always resolved, and not every one of these possible transitions is allowed, which is why we only see 6 lines. So how is Mossbauer spectroscopy used in bioinorganic chemistry? Well, if you have an iron and you have a Mossbauer spectrometer, you're going to look at it. And so this example spectrum shows the absorption versus source velocity in oxidized and reduced rubidoxine model complexes. They were preparing model complexes in order to see if the proposed structure was matched the spectroscopic data for the biological enzyme. This was before we knew the structures of the enzyme, before we had crystallography. So Mossbauer spectroscopy is useful when we don't have X-ray data. It's also useful to characterize and explain the spectroscopy for a structurally characterized species. When we look at the difference between A and B, A is a oxidized, so iron 3, and we saw that iron 3 has a lower isomer shift, so pretty small, less than a millimeter per second. Iron 3 has a larger isomer shift on the order of 3.5 millimeters per second. The lower spectra are from a ferredoxin protein, an Fe4S4 cluster. And since this technique is sensitive only to iron, we're only seeing signals due to the iron environment and not due to any of the other elements. And so in the reduced rubidoxin, we can see an iron, this is the oxidized. In the oxidized rubidoxin protein, we see a match to the model complex. And in the reduced rubidoxin, we see equal intensity of the larger isomer shift and smaller isomer shift species. So it suggests it's an iron 2 to iron 3 to complex. So the additional information you can get from Mossbauer spectroscopy in this context has to do with the oxidation states of the irons, which you can get from X-ray crystallography, although you need very good data. And protein data often is not going to be able to give you the bond length discrimination you would need to determine oxidation state. This spectroscopy shows that we have equivalent numbers of iron 2 and iron 3 in that ferredoxin protein. So this is the end of lesson 4 and the end of the experimental techniques. Next week we're going to look at the nitrogenase enzyme, family of enzymes, and explore applications of that, everything we've learned in bioinorganic chemistry to understand how that enzyme works.